Okay, so what I want to do today, as soon as I mute some other stuff here, is I want to keep going with the conversation that we had the other day on the different gates. So I showed you Digital Works at the end of class the other day, and I showed you a total of 3 gates, a NOT gate, an AND gate, and an OR gate. So I have 3 gates left, and I'm going to write the names of the gates up. I'm going to give you the diagram, and I'm going to give you the Boolean logic for them. Then I want you to use Digital Works to figure out what the truth table is and create a narrative describing the truth table. All right, so I'll give you about 10 minutes to do that. You can talk with your neighbor and stuff like that. So we also have a NAND gate. Think of it as a NOT AND gate. So we're going to have inputs of the A and B. It's going to come into an AND gate, except for there's going to be a circle. Every time you see that circle, remember that it means NOT. And a NOT gate is an inverter. So a NAND gate is a NOT AND gate, and then we go out to an LED output of X. The Boolean for this states X equals A and B NOTed, or you can put a bar across the whole thing. Now, since there's 2 inputs, and each input can be a 0 or a 1, that means we're base 2. So how many different states, since I only have 2 inputs here, how many different states do I need to test for? How many different inputs do I have? 2. 2 to the 2 is 4. That's not what I want. So A and B and X. So 0, 0, 0, 1, 1, 0, and 1, 1. So there's the 4 states. Then you're going to come up with that truth table. The next thing we have is a NOR gate. And for my NOR gate, I want to make this one a 3-input NOR gate. So whenever you test this to create the truth table, you need to test for how many different states? 8. It's always base 2. The exponent comes from the number of inputs that we have. So I want to say A, B, and C. It's still going to function exactly the same way into an OR gate with a little circle on the end, which again means NOT. To get the 3-input NOR gate, or NOT OR gate, you're going to right-click on the gate and go to inputs, and it'll allow you to change to 3 or 4. The Boolean looks like this. A, or X equals A or B or C NOTed. Since I have 3 inputs, A, B, and C, how many different states can that gate have? 2 to the 3rd. It's always base 2. Always. The exponent comes from the number of inputs that I have, or the number of characters that I have, or the number of bits that I have. It's 2 to the 3rd, so there's 8. 0, 0, 0. So I want to count from all zeros to all ones. 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. Those are the 8 states. That gate cannot have any other states. That's why computers are called finite state machines. It's an exacting, precise number, always. And then the last gate that we have is called an exclusive OR. Some people want to call it a XOR gate. It's called an exclusive OR gate, because that's what it is. An exclusive OR gate looks like this. I got an A and a B. It's going to come into something that looks like an OR except for there's an extra line. There's an extra line there to represent the exclusive OR. It says X equals A exclusive OR B. The exclusive OR is the little plus symbol with a circle around it that represents exclusive OR in Boolean's world. A, B, and X. I'm not even going to bother to ask how many states because I'm going to be deeply disappointed if you don't know. So, you bring up DigitalWorks. You play with that for a few minutes and see if you can get it taken care of for those truth tables. And then create a narrative on each one of those guys. Robert's not bad there. Give you just a few minutes to kind of figure those out. How's it going? Getting there? All right, let me have a look here to see how everybody's doing. I'd imagine not. So remember, a knot is an inverter, so you should be seeing that it's an inverted OR. So in an OR, everything's got to be 1 for the output to be 1. As soon as I add a knot on there, it inverts. So if everything's 1, the output should be 0. You should see that in Digital Works. Be right there. Mm-hmm. So what's a 0, 0 yield? Okay, so you put a 1 wherever 0, 0, or 1, 1 is. You put it in your notes in here for your NAND. So a 1, 1, so and 1, 1, although that shouldn't be the case. I'm not sure why that's lighting up. Oh, it's because you clicked pause. Unclick pause. There you go. Click on play. There you go. Yep. What's up? It's under Canvas. I can send it to you in a minute. Oh, that's distracting to you. Look at that. You even looked at it. Oh, you. Uh-huh. Want to become a less distracted student? Stop allowing your phone to bug the hell out of you all day long. Does it vibrate? And every one of your apps on there wants your attention too. Pick me, click me, pick me, click me, pick me, click me. Exactly. That's what I tell people all the time. Like, I feel like I'm so distracted by my phone. I'm like, you're in control of the damn phone. Well, so is Twitter, and some of these games are insane too. You know, feed my animal. Like my kids, every once in a while they'll download a game and they'll click on allow instead of don't allow. So I've been trying to train them to click on don't allow. And they'll be like, feed your dragons. I'm like, let the dragons die. They don't exist. That's everybody but me, because I knew about this a long time ago. That's why my list of people that I'm not friends with is much longer than my list of people that I'm friends with. All right. So all you got to do is tie into the API just once, and you can see how much information you give out to people and get from people. Once. Read the API documentation. All right. A not AND gate. An AND gate says that everything's got to be true for the output to be true. Well, this is a not AND gate, so that's inverted. So it should be 1, 1, 1, 0. Now, if that confuses you, take the not off and just do an and. So you would write 0, 0, 0, 1, and then invert that column, right? 1, 1, 1, 0. You're going to do the same thing for the or. So an or says if anything is true, the output is true. But we're going to invert that so that where it was anything was true, the output is true. If anything is true, the output is false now. All right? So all zeros actually yield a 1 here, and everything else is going to be 0, 0, 0, 0, 0, 0, 0. It's an inverted or. Inverted or, not or. Now the exclusive or, I haven't asked you for a narrative on the other ones. I've given you the narrative. So an exclusive or, as you played with it in Digital Works, you should have seen it be 0, 1, 1, 0. What's the narrative for that? How do you describe that truth table? Okay, so it only turns on, it's only true when it's both a 1 and a 0. I want to rephrase that just a little bit. You're 100% correct. It's only true when both states are present, meaning a 0 or a 1. Okay? Any other time when it's all zeros or all ones, it's a 0. So that looks pretty good. Questions? Everybody's pretty good. Anybody? Okay. So the next thing that I want to show you is we take these and we start putting them together to create these things called combination circuits. All right? In combination circuits, we then put into ICs, integrated circuits. So I have with me today a little something that I'll show you. I have this pretty cool pretty cool thing. It's called a virtual Vulkan trainer. Oh man, all my jumpers just fell out all over the place. You did that, didn't you, David? I knew it was you, man. At least you owned it, dude. What the hell? Now, hold on, I'm cleaning up my mess. Give me just a minute here. I'm sorry, I'm cleaning up David's mess. Yeah, man! Yeah, that's an annoying ringtone. Yeah. All right, I think I got it. Pretty close. Just don't close it up. No, they're not. Okay, so what I have here is, this is called a virtual Vulkan trainer, and we used to use this in 365, but we don't use it in 365 anymore. So we use Raspberry Pis. So these are the integrated circuits that I was talking about. These are actually 7400s. Every single chip you're ever going to encounter is going to have a number associated with it. So if you went out right now and you search for ICs 7400s, you're going to get that particular chip. So what is a 7400? Up here at the top, it'll tell you it's a quad 2-input NAND gate. So that means there's 4 NANDs that are 2 inputs each on these. And then there's a pinout on here as well. We can see the different pinouts And those pins have VCC, ground. It'll tell you what the inputs are for each gate and what the output is for each gate so that you can start plugging these into your breadboard over here. So we can take and plop those into the breadboard to do whatever it is we need to do. You actually wouldn't put it in that way. I should have probably done that, but that's okay. Across the top, you'll see other things. For example, here is the VCC, meaning the power running down to our breadboard. Here's our power supply, right, a 9-volt. Across the top, we have some LEDs. We also have a 7-segment display across the top with some different switches that we can turn things on and off. I'll pass this around as you get to like Digital Logic 365. Again, we start using Raspberry Pis now. We've abstracted some of this out because it's just not necessary as it used to be. It used to be pretty necessary to understand things at a much deeper level. But for us, we don't need to understand it quite as much. But I'll pass this around so you can have a look at things and see some of the different hardware that we're talking about. All right. So let's make a combination circuit. So we're just going to make a simple combination circuit. Whenever we do that, we're going to do the truth table, which tells us what the purpose of that particular circuit is. So I actually have one made up here somewhere that I'd like to use. So this particular circuit is going to have 3 inputs, A, B, and C. Don't put this into DigitalWorks right now. You can try it out later. It's going to have an AND gate up top, and then it's going to have an OR gate down below. Both of these are going to come out and go into an exclusive OR gate, which is going to lead out to an LED called X. My A and my B are going to go into this top AND gate. My B is going to come down to this OR gate, and my C is going to come down to this OR gate. I'll give you a minute to write that down. It's an OR gate, yep. Everybody got it? Got it down enough now? Aaron, this program is on Canvas. Let me push it out to you real quick while I'm thinking about it, to your computer. And there should be a new folder on your desktop already there called Land School Files, and it's inside of there. You got to extract it, and then you can use it. All right. So I got 3 inputs, A, B, and C. What are the different states that this circuit can have? How many? 8. Why 8? 2 to the third is 8. So what are the states? I start at 0, 0, 0, and I go to 1, 1, 1. So 0, 0, 0, 0, 1, I'm sorry, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. Now, we're creating the truth table, which tells us what this circuit does based on the states of its input. There are 8 different states for the inputs. Depending on what the input state is, it will tell us if there's an output or not. So the first one we're going to do is this AND. We got A ANDed to B. So I say A and B. So I come over and I make a new column called A and B. And I look at my A and my B inputs, and I AND those together. And we know that the properties of an AND gate state that both inputs must be true for the output to be true. So 0, 0, 0, 0, 0, 0, 1, 1. Everybody understood what I did, right? I looked at my A column and my B column, and I ANDed those together. That's all I did. You good, Randy? All right. The next one, I moved left to right, top to bottom. I have to solve that OR before I can address the exclusive OR. So this particular one is B ORed to C. Now I'm making a lot of extra notes up there, and you should do the same in your notes. But as you get it, you don't have to write it all out like I'm doing. So here, I want to look at my B column, and I'm going to look at my C column, and I'm going to OR those 2 columns together. Now, Sean, the properties of an OR gate state that
one or the other.
There you go. If there's a 1 present, the output is 1. So I look at my B and my C column, and I say 0, 1, 1, 1, 0, 1, 1, 1. Now, upon completion of the truth table, I'm also going to know what the Boolean is for my circuit. So for this exclusive OR, this is A and B. So the input is A and B. That's where I'm getting that from. And I'm exclusive ORing that to the B or C output gate. So I'll come over and I'll make a new column here. A and B exclusive ORed to the B or C. Exclusive OR says both states must be present. So 0, 0 is a 0, 0, 1 is a 1, 0, 1 is a 1, 0, 1 is a 1, 0, 0 is a 0, 0, 1 is a 1, 1, 1 is a 0, and 1, 1 is a 0. So I got a minute or two to take that and throw it into DigitalWorks so you can see this working. So I'll take it and I'll throw it into DigitalWorks. Man, that seems like a hard ringer to turn off. I think it's funny when like the president or the provost, that happens in the middle of a meeting. They're like all embarrassed and their face turns red. All right, so here we go. Just so you can see that this is the case. Let me throw my screen up on yours. So I got three inputs, A, B, and C. A, B, C. Got an AND gate. Got an OR gate. Got an exclusive OR gate. Then I got an output for my LED of X. Wire that guy up. I have a little bit more experience with this program than you do, so don't worry about it. So I'm going to click on play. It says that if I enter in a 1, 1, 0, I should get a 0. So 1, 1, 0, I get a 0. If I put in 1, 0, 1, 1, 0, 1, I should get a 1, and I do. If I put in 0, 0, 1, 0, 0, 1, I get a 1. 0, 1, 0, I get a 1 as well. All right? So the truth table always tells us precisely what the outcome of a circuit is. You good, Dylan? You look lost, man. You sure? Yeah. Do you have any questions?
Not right now.
That was a very confused look. Or maybe you were zoning out for a while and you just came back and you're like, oh crap, where'd all that come from? Is that what it was? You on Twitch again? See, I didn't even call you out this time. What's up with that? Come on, Patrick. That's good, man. What's up? Which ones did you click for what? I'm sorry. No, I know you do. All you got to do is just kind of hover over them, and they'll tell you what they are. Hold on. If you just kind of hover, well, you can't see because it's actually on the other screen. They're all coming over on the other screen. Let's do it this way. See how it tells you what they all are. So here's the interactive input, and here is the LED, and then this is the wiring tool. Okay, there you go. Okay, so I want to keep on going. The circuit that I have up here right now is just kind of a demonstration circuit. Perhaps this could be a combination circuit, right? So I want to introduce this idea of this thing called a hash, right? It wouldn't be a very good hash because we have actually 4 collisions showing up. So what a hash is a one-way function that takes a message and produces a fingerprint of the message. And the message could literally be your password or something like that, but it could also be a file. So every time we compare the fingerprints of the original message, it should be the same. Well, in this particular case, there would be 4 fingerprints for 4 different messages. Message 001, message 010, message 011. As we get better with hashes, as we discover more collisions and we have more computing power to discover those collisions, we depreciate those hashing functions. Okay? So in this particular case, it wouldn't make a very good lock. It wouldn't make a very good anything. So it's just an example educational piece to help you understand a truth table. So let's now have a look at a real circuit. Something that is used in every single device you own that's digital. So this particular circuit is going to have two inputs, A and B. This is a real circuit that exists in every single digital piece of electronics you have. It has an exclusive OR gate, and it has an AND gate. Both of my inputs go to both of my gates. When you see the dot, that means that I'm connected to that wire. When you see the little arc like that, that means that I'm jumping over that. Computer programs don't need to do that. We need to do that as human beings. We make that little jump there. That means that it's not connected for sure. I want to have two outputs on this particular circuit. I want to label one of them as sum and the other one as carry. This particular circuit enables us to add together two bits of information. All right? Let's create the truth table to see what it does. So I have input A, I have input B. Oh, what am I doing? I have input A, I have input B. Two inputs, 0, 0, 0, 1, 1, 0, 1, 1 can hold four states, 2 to the 2. I have an exclusive OR, so I'm going to say A exclusive OR B. I also refer to that as sum. That says that if any of the input or both states must be true for the output to be true. So that's 0, 1, 1, 0. And then I have that carry, which is an AND. So that's A ANDed to B. I'm going to call this carry. Properties of an AND gate say that both inputs must be true for output to be true. So 0, 0, 0, 1. That's my truth table. That's the whole truth table. So I'll let everybody get that in your notes, and then we'll talk about it. Okay, here we go. So it's about adding two bits together. So I have bit A and I have bit B. All right? Two different numbers. 0 plus 0 is what? 0. Is there a carry? No. 0 plus 0. Sum of 0, carry of 0. What about 0 plus 1? What's 0 plus 1? 1. Is there a carry? No carry. Sum of 1, carry of 0. 1 plus 0, same thing. Sum of 1, no carry. What about a 1 plus 1? Remember, this would be my A bit and my B bit. So I would make this a 1 and this a 1. It's going to give me a sum of 0. It's going to actually light up as a 0. Not light up, so it'll be a 0. But we're saying that a 0 goes there with a carry of 1, and we bring it down, so it would be a 1, 0. So a sum of 0, carry of 1. And that's all fine and dandy if you're adding 2 bits together at the ones place. I'm giving some hints here. At the ones place, that's great. But what happens if I say 1, 1, so that's my A number, that's my A bit string, plus a B bit string of 1, 1. Ones place, I can plug this in. 1 and 1. It's going to yield a 0 with a carry of 1. When I get to my 2's place, I can still plug my 1 and my 1 in, but what about my carry? Where do I plug my carry in to my circuitry? You don't. You don't plug it in, because there's no input for a carry. You with me? So that's why this is called a half adder. It's only used in the ones place in our circuitry. Everybody got my truth table for that? All right, so here is your homework for Monday. You need to come up with the truth table and put the following into DigitalWorks and try it out. It's a lot of delay going on. So you're going to put the following in. This is a full adder. A full adder is made up of 2 half adders. Okay? So I want to put my 2 half adders in. I got an exclusive OR, and I got an AND. And that's going to be hooked up the same way. So it's going to go in like that, and then down to that one as well. So that's my first half adder. Now after that, things are going to get a little weird. I want to put my other half adder in. And I'm going to put one more gate in. I'm going to put an OR gate in down here. And the output of both of the AND gates from the half adders is going to go into that OR down there. And we're going to call that output carry, meaning carry out, and we will have an LED, or that will carry out and into another carry in. So up at the top, I want to have another carry in input. So that's going to be an input up there. C in. The output from this exclusive OR needs to go into both of these guys. And then the carry in needs to go in here and in here. This I'm going to call sum. I'll give you a minute to get that in your notes, and then we'll talk about it for just a minute. Doesn't class go fast when you're watching Twitch? I mean, having fun? Twitch does? I wish I had time to watch Twitch. I'll leave it up here so you can take a picture of it on the way out if you like. How many inputs are on there? How many inputs do I have? How many? Wasn't you that mumbled? What are they? A, B, and carry in. So if there are 3 different inputs, how many different states can that circuitry take? 8, right? 8. All starting at 0, 0, 0, 0 through all 1s. So as you create your truth table, again, you're going to move left to right, anding together the different items as you calculate them. So in the very beginning, you got A and B and C with that with your inputs already laid out. I would look at this exclusive OR, and I would exclusive OR together the A and the B column. Same thing for my AND gate. When I get to here, I'm exclusive ORing together the output of this exclusive OR, so that'll be a column that already exists, to this carry in. And then the same thing down here, the output here and the CN here. And then I'm going to OR the output, so the column that represents the output of this and the column that represents the output of this. That's going to tell me my overall state of everything. Now, one of these full adders can accept a carry in and will tell us what the sum and the carry out would be. If I want to begin to add together multiple digit numbers like this, I would need a new full adder for every place value. So one for the 1's place, one for the 2's place, one for the 4's place, the 8's place, 16's place, 32's, so on and so forth. So on Monday, I want to walk around. I want to see the truth table. And I want to see it in DigitalWorks. I want you to put it in DigitalWorks and get it working. All right? I'll grade that real fast on Monday. Don't forget, DigitalWorks is available to you on Canvas under Files. You can download it on your home computer. If you have an Apple, it won't work. All right? But any of your Windows machines will. You still do it in the 24/7. You can download it and just extract it on the desktop and it'll work just fine. I'll see you Monday. It's supposed to be a nice afternoon.